Hi, I'm going to talk to you about learning to drive from a world on rails. This is joint work between Diane Chetton, Fladden Colton, and Philip Cranbill. Here, we look at the problem of autonomous navigation from sensor inputs alone. The agent's goal is to navigate from point A to point B without an incident. It does so by using images and high-level navigational commands as an input. You can think of these commands as sort of instructions you get from a GPS or Google Maps. The agent's output then is steering, acceleration, and braking for every single time step. For human drivers, this is a fairly effortless task given its sufficient rest. For machines, however, this has been proven tremendously difficult. One of the primary reasons for this is that driving involves two very difficult subtasks. First, learning to perceive our environment, and then second, learning to act on the perceived signal. The primary difficulty in these tasks is generalization, namely learning a perception system and driving policy that is able to deal with arbitrary unseen environments during deployment. For perception, many papers in this and other vision conferences already make great progress towards tackling generalization in the visual domain. The general idea is simple. We use supervised learning, we pair it up with heavy data augmentation that reflects the invariances we expect from the test domain, and finally, we collect a large enough dataset to train our vision system on. The general approach is starting to yield vision systems that are robust enough to drive. The same is not true for policy learning. There's a long tail of odd driving behaviors, corner cases, and dangerous maneuvers. Many of these situations are safety critical and mistakes are costly. While we have large datasets of driving behaviors, they're usually called driving logs, they're unlikely to cover all scenarios we ever want to cover, and they are hard to generalize, primarily because we don't know any good ways to do data augmentation on them, and supervised learning alone might not be enough. The supervised learning paradigm for policy learning is called imitation learning. Here we are interested in finding a policy that maps our current state or observations to actions. We do this by first collecting a large dataset of human drivers acting in the real world. Then we learn a policy that mimics the human driver's behavior. This approach was pioneered by Alvin out of CMU, where a shallow neural network was able to drive a military ambulance for about 2 to 3 miles per hour completely autonomously. If we take the same approach and strap it onto our current autonomous vehicles, it will hopelessly overfit. The main issue is that from imitations alone, the car will not learn to recover or generalize from observations that do not follow an ideal driving path. A common fix to is to train with noise injected into the training data. Or train a pair of policies where the first policy uses a compact ground truth state as an input and thus learns to generalize, while a second one imitates from much richer supervision. Overall, imitation learning is simple and effective. However, it only supervises ideal actions for each state. It does not know what other actions might also work. It also doesn't know which failures are critical and which failures just lead to slightly suboptimal behavior. It struggles to generalize if the test distribution drifts away from the training distribution. Reinforcement learning offers a solution here. Instead of relying on human actions, the agent gets to explore the environment itself and can come up with an ideal combination of actions for a driving policy. The way this works is that we again learn a policy that maps the state or observations to actions of the agent. But this time, we also get a transition function. This transition function tells us that if we are in a state, take a specific action, where are we going to end up? You can think of this transition function as either a simulated or a real vehicle moving around in the world. We then define a reward function that sort of encourages good driving behavior and penalizes unsafe driving behavior or crashes. And finally, we just optimize an objective that says that over time, we would like to maximize the reward that our agent's actions get. Reinforcement learning can, in theory, find better than human policies. However, in practice, it is very data inefficient. It relies on a potentially dangerous exploration phase where the algorithm tries arbitrary actions to estimate their outcome and reward. Offline reinforcement learning addresses this shortcoming and instead runs the algorithm on a pre-recorded dataset of offline driving logs. The overall setup is very similar to imitation learning. We use an offline dataset, but additionally learn the transition function from this offline data. This transition learns to simulate the world forward and replaces the active exploration of reinforcement learning. We then again maximize the expected reward of our policy under the learned transition model. This approach has many of the appealing properties of imitation learning and reinforcement learning. We start with a static dataset, thus avoid dangerous exploration, and we're able to learn better than human policies. It obviously comes with a catch. Learning a good transition model is hard. After all, even simple open source driving simulators have hundreds of thousands of lines of code, and trying to jam all of this into a deep network is simply too difficult. So what do we do? In this paper, we make a very simple and provocative assumption. What happens if we assume that the ego vehicle is somewhat independent of the world? And what I mean with this is, what happens if the agent can see the environment and react to it, but its actions can only influence itself? So the agent can only change its own state, and the world will not react to anything the agent does. We call this assumption the world on rails assumption. Now, this assumption is obviously not true in all traffic scenarios, but let's still see where this leads us. Since the world does not react to the agent, we can simply replay it from our dataset. It does not depend on the agent's state and does not need to consider its actions. On the other hand, the forward model for the ego vehicle is very compact and can afford efficient exploration. However, it can only change its own state and not the world. How do we use our world on rails assumption for reinforcement learning? Let's start with a standard Bellman update that recursively defines a value function. The value describes how desirable a certain state is. Good driving is desirable, thus has a high value. A state that leads to a crash is not desirable and thus has a low value. The Bellman update defines this recursively by adding a reward, taking one step into the future and figuring out where a certain action would take us and how good the state is. Let's now plug in the world on rails. This far, nothing changed. The Bellman updates still look one step into the future to determine the next best state. However, here only the ego vehicle is a free variable. The world is modeled by replaying data, and thus can be a constant. This simplifies the Bellman update to a recursive definition of the value function through time. Each value now only depends on the state of the ego vehicle, and all the world state disappears in the time index. What have we gained through this? The ego vehicle state is small enough to discretize in a table. This leads to a very efficient evaluation of the Bellman update through dynamic programming. The value at time t is defined as the maximum over all actions of the rewards that we collect choosing that action, plus the value at time t plus 1 displaced by the transition function of the ego vehicle. This recursively defines the value at time t as a function of the value of time t plus 1. Given the value at time t plus 1 in tabular form, we simply enumerate all possible states at time t and evaluate this equation. We then walk backwards through time until all states have a dense annotation of their value. This simple tabular evaluation then allows us to find the optimal driving behavior for the ego vehicle in all of our driving logs. However, it does not yet yield a policy. We obtain a driving policy by first collecting offline driving logs. We use a built-in autopilot in our simulator, but a human driver will likely also work. We then learn a forward model of our vehicle. In our case, we learn the parameters of a bicycle model. We then compute the value function using the Bellman updates for k time steps into the future. And finally, we use the values to predict the outcome of all actions for each specific data point collected in our driving logs. We further augment our data by trying all driving speeds, all high-level commands, and a limited set of different orientations for the vehicle. For each training example, we now get much richer supervision from our value function. This leads to a more robust driving policy. We evaluate our algorithm on the CARLA NoCrash benchmark. Here, the metric that we evaluate is success rate. How many times are we able to drive from a point A to the point B in a test map without any collisions? We compare our algorithm to two baselines, a reinforcement learning baseline by Toromanov et al. And learning by cheating. Our new approach performs significantly better than both baselines. We also evaluate on the CARLA Leaderboard. Here the metric is a combination of route completion and infraction score. This combination is often referred to as driving score. For the CARLA Leaderboard, we rely on a GPS sensor, an IMU, RGB cameras, and speedometer. We do not use LiDAR or radar. On the CARLA Leaderboard, we significantly outperform all prior entries. Finally, we evaluate our algorithm on the ProcGen benchmark. Here we compare on the games Maze and Heist. For both, we outperform the state-of-the-art model-free reinforcement learning algorithms using about a fifth of the training data. Thank you for your attention. Code and data used in this project is available online.